Hello and welcome to Math Zone, brought to you by African Motives. Today, we're diving into the nated Electrotechnics N4 curriculum, starting with the fundamentals. By the end of this video, you will be able to define key electrical concepts and apply them to practical problems. Before we begin, let's take a look at our roadmap for this entire module. Understanding this structure will help you follow along as we explore each topic in detail. We'll start with the basics, including important concepts like current and resistance, and the famous Ohm's law. Next, we'll build on those ideas to cover resistor and cell combinations, the factors that affect resistance, and essential network theorems from Kirchhoff, Norton, and Thevenin. Then we'll move into the world of magnetism and electromagnetism, electromagnetic induction, and finally, capacitors. These topics form the backbone of modern electrical engineering. Today, we'll focus on the introduction to electricity. Specifically, our learning objectives for this lesson are to define current potential difference, electromotive force, and resistance, to calculate current, voltage, and resistance using Ohm's law, and to calculate power and heat energy in a circuit. Let's begin with the most fundamental concept. Our first topic is electric current. What is it really? Electricity is defined as the flow of charged particles. In metal conductors like copper wires, these charge carriers are electrons. Specifically, they are the electrons in the outermost shell of an atom called valence electrons, which are excited and flow in an organized direction. This directed movement of valence electrons is what we call current. We represent current with the symbol I and measure its magnitude in units called amperes, or A for short. 1 ampere is defined as the flow of 1 coulomb of charge per second. A coulomb is simply a quantity of charge. So, an ampere measures how much charge is flowing past a point each second. Now, why is current so important? What does it do for us? Electricity, through current flow, produces several crucial effects. It provides lighting, like in our homes and street lamps. It generates heat, which is how appliances like electric kettles and heaters work. And it produces chemical effects, as seen in batteries and electrolysis. Finally, current creates magnetic fields, a principle that drives motors and generators. So, to recap this section, current is the flow of electrons. It is represented by I and measured in amperes, and its effects are what make modern technology possible. But what causes this flow? The answer lies in the concept of potential difference. We've established that current is the flow of electrons. But what makes electrons move? Imagine a water pipe. Water won't flow unless there's a pressure difference between two ends of the pipe. Similarly, electrons in a circuit won't flow unless there's an electrical pressure. This pressure is what we call potential difference, or terminal voltage. Formally, potential difference between 2 points is defined as the work done per unit of charge moved between those points. Let's break that down. Work in physics is energy transferred. So, potential difference is the energy that is given to a charge to move it from one point to another. It's the push that gets the current flowing. In simple terms, potential difference is the electrical pressure that produces current flow in a closed electric circuit. What are the units for potential difference? Since work is measured in joules, J, and charge in coulombs, C, we get joules per coulomb. This unit, joules per coulomb, is so common that it has its own special name, the volt, symbolized by V. So 1 volt means that 1 joule of energy is required to move 1 coulomb of charge. It's the standard unit for measuring electrical pressure. In this section, we defined potential difference as the work per unit charge, which is the electrical pressure driving current. We learned its symbol is V or PD, and its unit is the volt. While potential difference refers to the voltage across the terminals of a circuit, another related term is electromotive force, or EMF. Electromotive force is the electrical potential produced by any source of electrical energy. You might hear the word force and think it's measured in newtons, but it's not. That's why it's considered a misnomer. EMF is a form of potential, so it's also measured in volts. So, if both EMF and potential difference are measured in volts, what's the difference? Let's clarify this crucial point to avoid confusion. Consider a simple circuit with a battery and a light bulb, but the switch is open. Since the switch is open, the circuit is incomplete. No current can flow. The light bulb does not glow. If we were to measure the voltage across the battery in this state, that measurement would be the electromotive force, or EMF. Now let's close the switch. The circuit is now closed, current I is flowing, and the light bulb glows. At this moment, if we measure the voltage across the battery, that measurement is the potential difference, or terminal voltage. In an ideal world, the EMF and PD would be the same. But in real-world components, some energy is always lost within the source itself due to its internal resistance. Therefore, the potential difference, the voltage available to the external circuit, will always be slightly less than the EMF. So, to recap, EMF is the source's potential with no current flowing, and potential difference is the actual voltage available when current is flowing. Where does this EMF come from? There are many sources. Common sources include cells and batteries, generators that convert mechanical energy to electrical, solar panels that convert light, and even heat or friction. These sources all work to establish that electrical pressure to get current flowing in a circuit. So far, we have our source, the electromotive force, which creates electrical pressure, the potential difference. This pressure pushes the current, the flow of electrons. But in any system, there is opposition. Every material in an electric circuit offers opposition to the flow of electric current. This opposition is called resistance. Think of it like friction. Just as friction opposes motion, resistance opposes the flow of electrons. As electrons push their way through a material, they collide with atoms, losing some of their energy along the way. This energy loss is why resistance causes a heating effect. The collisions convert electrical energy into heat energy. We represent resistance with the symbol R, and its standard SI unit is the ohm, represented by the Greek letter omega, O. The ohm is defined as the resistance that allows a current of 1 ampere to flow through it when a potential difference of 1 volt is applied across it. Now, let's classify materials based on their resistance. First, we have conductors. These are materials that allow current to flow through them easily. They have very low resistance. Good examples are gold, silver, copper, and aluminium. On the opposite end are insulators. These materials have extremely high resistance and do not allow current to pass through them easily. Think of glass, paper, rubber like PVC, and ceramic. These are used to protect us from electric shocks. Interestingly, there are materials called semiconductors. Their conducting properties lie between those of conductors and insulators. Materials like germanium and silicon are used to manufacture solid-state components like diodes and transistors, which are the building blocks of modern electronics. So, if conductors are so good, why would we want resistance? It seems to get in the way. The answer is that resistance is not always a bad thing. It serves two important purposes. First, resistance is needed to produce voltage drops. In a circuit, we often need different voltages at different points, and resistors help create these. Second, and perhaps most importantly, resistors are used to limit the current flow to a safe level for other components in the circuit. If there was no resistance, the current could become infinite and destroy the components. To summarize, resistance is the opposition to current flow, measured in ohms, and is crucial for controlling voltage and limiting current in a circuit. So, we have potential difference, current, and resistance. These three fundamental quantities are not independent. They are connected by a powerful and simple law. This brings us to Ohm's law. Ohm's law describes the relationship between these three variables in any closed circuit. Let's break that down. Directly proportional to the voltage means that if you increase the voltage, the current will increase, as long as everything else stays the same. Inversely proportional to the resistance means that if you increase the resistance, the current will decrease. This makes intuitive sense. A bigger push means more flow, and more opposition means less flow. Mathematically, Ohm's law is expressed as this simple formula: I equals V divided by R. Let's remind ourselves what these symbols represent. Here, I is the current in amperes, R is the resistance in ohms, and V is the potential difference in volts. A very useful tool for remembering Ohm's law is the Ohm's law triangle. If you need to find one of these variables, you can simply cover it up in the triangle, and the remaining two show you the formula. So, if you want to find V, You cover V and you're left with I next to R. That means V equals I times R. If you want to find I, you cover I and you're left with V over R, so I equals V divided by R. And if you want to find R, you cover R and you're left with V over I, so R equals V divided by I. This triangle makes it incredibly easy to rearrange the formula for any variable you need to solve for. Let's put Ohm's law into practice with a classic example. Example 1.1 states, a 400-watt incandescent light bulb is connected to a 240-volt supply. First, let's identify what we're given. We have power, P, which is 400 watts, and potential difference, V, which is 240 volts. Our first task is to calculate the current drawn by the bulb. To do this, we'll use the power formula P equals V times I. Remember this formula, as it's just as important as Ohm's law. To find current I, we rearrange the formula to I equals P over V. Substituting our values, we get 400 divided by 240. The result is 1.666 amperes. As the exam tip suggests, we should round this to 3 decimal places. So, the current is 1.667 amperes. Next, let's calculate the resistance. Part B asks for the resistance of the light bulb's element. We can do this in 2 ways. First, using the current we just calculated in Ohm's law. From our Ohm's law triangle, we know that R equals V over I. Plugging in V equals 240 and our calculated I of 1.667, we get approximately 143.971 ohms. The second method is often more accurate because it uses the original given values. We can use the power formula P equals V squared over R. Rearranging for R, we get R equals V squared over P. Substituting the original values, 240 squared divided by 400 gives us exactly 144 ohms. This is the more precise answer. Now let's expand our understanding of electric circuits to include energy. Energy is the capacity to do work. When we have an electric current flowing through a resistor, we saw it produces heat. This is a conversion of electrical energy into heat energy. James Prescott. Joule was an English physicist who studied this heating effect, and he formulated Joule's law in 1842. Joule's law states that the heat generated in a circuit is proportional to 3 things: the square of the current, the resistance of the circuit, and the time during which the current flows. In formula form, Joule's law is Q equals I squared RT. Heat energy Q is in joules. J, current I is in amperes. A, resistance R is in ohms. Os, and time T must be in seconds. S, since we know that power is the rate of energy consumption, P equals Q over T or Q equals P times T, we can derive other useful formulas for heat energy. By substituting our various power formulas, we can also say that Q equals V squared over R times T, or Q equals VIT. Having these different formulas is incredibly helpful as it allows us to calculate energy regardless of which variables we are given in a problem. Let's revisit our first example and calculate the energy dissipated. Remember the problem: a 400-watt bulb on a 240-volt supply. Now, let's calculate the energy dissipated in 1.5 hours and express the answer in megajoules. First and foremost, we must convert the time into seconds. This is a critical step in almost all electrical calculations. To convert 1.5 hours to seconds, we multiply by 60 to get minutes, and then by 60 again to get seconds. 1.5 times 60 times 60 equals 5,400 seconds. Since we were given the power P directly as 400 watts, the easiest formula to use is Q equals P times T. Remember, power is energy per second, so energy is power times time. Substituting the values, 400 watts times 5,400 seconds gives us 2,160,000 joules. The problem asks for the answer in megajoules. 1 megajoule is 1,000,000 joules. So, to convert joules to megajoules, we divide by 1 million. 2,160,000 divided by 1,000,000 gives us 2.116 megajoules. That's a significant amount of energy dissipated as heat and light. You could have also used the formula Q equals I squared RT, and as you can see from the calculation in the text, it gives the same answer, just with slightly more rounding error because we used the rounded value for current. This reinforces that using the original given values is always the best practice. Our final topic for this introductory class is the concept of energy billing. We've seen how to calculate energy in joules or megajoules, but if you look at your electricity bill, it's not in joules. The joule is a very small unit of energy. Calculating household consumption in joules would lead to enormous numbers. So, electricity supply authorities bill consumers using a different unit. They use the kilowatt hour, or kWh. This is commonly referred to as 1 unit of electricity. It's simply a more convenient unit for billing large amounts of energy. But how does the kilowatt hour relate to the joule? Let's figure it out. A kilowatt is 1000 watts, and an hour is 3600 seconds. So, 1 kilowatt hour is equal to 1000 watts times 3600 seconds, which gives us 3,600,000 joules. That's 3.6 megajoules. So, when you consume 1 unit of electricity, you are consuming 3.6 megajoules of energy. Now, let's see how this is used in an example. The notes provide tariff information for the city of Chuani from 2018-2019. We see the domestic tariff is 167 cents per kilowatt hour, and the industrial tariff is slightly lower at 108.87 cents per kilowatt hour. We'll use this information in our final example. Let's work through a comprehensive example that brings together everything we've learned. Example 1-2. An electric hairdryer has a 32-ohm heating element and dissipates 1.725 megajoules of energy in 17 minutes. First, let's list our given values, and remember to convert them to SI units. Resistance R is 32 ohms. Energy Q is 1.725 megajoules, which we convert to joules by multiplying by 1 million. Time T is 17 minutes, which we convert to seconds by multiplying by 60. Part A is to calculate the time in seconds. We've already done this. 17 times 60 is 1020 seconds. Part B is to calculate the current drawn. We have energy, resistance, and time. This points us to Joule's law. Q equals I squared RT. Rearranging to solve for I, we get I equals the square root of Q over rad. Substituting the values, we calculate the current to be approximately 7.272 amperes. This is a lot of current, typical for a powerful heating appliance like a hairdryer. Now let's find the voltage. Part C asks for the supply voltage. Again, 2 methods. The simplest is using Ohm's law. V equals I times R. Using our calculated current and given resistance, we get 232.576 volts. A more precise calculation using Q equals VI, it yields 232.545 volts. The slight difference is due to rounding our current value. In a test, either would likely be acceptable, but using original values is safer. We're in the home stretch of our hairdryer example. For our final calculation, Part D asks for the cost to operate the hairdryer for this 17-minute period, given a unit charge of R116. To find the cost, we need to know 2 things: the power of the hairdryer in kilowatts and the time it was used in hours. First, let's calculate the power. We can use the power formula P equals VA times I. Plugging in our calculated voltage and current gives us approximately 1690 watts. Now we convert this power to kilowatts. A kilowatt is 1000 watts, so we divide by 1000. This gives us approximately 1.69 kilowatts. Next, we need the time in hours. The hairdryer was on for 17 minutes. To convert minutes to hours, we divide by C, so the time of usage is approximately 0.283 hours. We now have power in kilowatts and time in hours, so we can calculate the units of electricity consumed, which is the kilowatt hours. Units consumed equals power times time. 1.69 kilowatts times 0.2183 hours is approximately 0.478 units. Finally, we can calculate the cost. Cost of electricity is the units consumed times the charge per unit. 0.478 units times R1.66 per unit gives a total cost of R0.79. Or, in cents, that's 79.35 cents, which we round up to 80 cents. So, running that powerful hairdryer for 17 minutes would cost you around 80 cents. Let's quickly review another important concept before we conclude. Efficiency is a measure of how well a machine transforms energy or power. It tells us how much of the input we put into a system we actually get out as useful output. The formal definition of efficiency is the ratio of power output to power input. Remember, no real-world machine is 100% efficient. There are always losses, often in the form of heat, due to resistance or friction. The difference between the input power and output power is the power lost. The formula for efficiency is EAT, the Greek letter for N equals power out divided by power in multiplied by 100 to get a percentage. In an electric motor, for instance, the electrical power you supply, P in, is converted into mechanical power to turn something, P out. The motor is never 100% efficient. Some of that electrical energy is lost as heat in the motor's windings. So efficiency is a crucial concept for engineers, helping them to design systems that minimize waste and maximize useful output. Let's take a moment to recap what we've covered in this introductory class on the principles of electricity. We aim to define key electrical concepts and apply them to practical problems. First, we defined current, I, as the flow of electrons, measured in amperes. Then, we discussed potential difference, PD or V, which is the electrical pressure measured in volts. We distinguished it from electromotive force, EMF, which is the voltage of an open circuit source. We introduced resistance, R, which opposes current flow and is measured in ohms. This led us to the fundamental relationship between these three. Ohm's law. We also learned about electrical power, P, measured in watts, and heat energy, Q, measured in joules, along with Joule's law describing the heating effect. Finally, we explored energy billing using the kilowatt hour and worked through two comprehensive examples that required us to define, calculate, and convert these quantities. You have now met all the learning objectives we set at the start. In our next video, we will continue to build on these foundations as we begin to analyze resistors connected in series and parallel. Thank you for joining Math Zone, African Motives.